All right, everybody, how we doing? Doing good, doing good. How's the semester going? Not too bad. A little busy. Not busy at all. Sleepy. It's okay. I just finished grading your guys' assignments. What's his name? Let me grab my water bottle. So far everyone did pretty good. I really enjoyed the lab, the format you guys do. I'm very casual. I'm very pretty chill with grading. But what's his name? I had like a few students. First off, I think everyone's cadence in here should be normal. I think we fixed all the problems. There was one guy, he had a network issue, but it was his house. There was like a weird firewall. I don't know what the heck was going on. But other than that, everyone's cadence shouldn't be broken. So I had someone finish the assignment and they're like, I couldn't finish the experiment because I saw a DRC, I looked at it and didn't do anything about it. I'm like, yeah, DRCs are fun. DRC, it's the best part. Okay, I'm not well. No DRCs are good. But what's his name? Let me go over what we did. I wanna mimic someone's solutions. Tap tap tap. Come on. Hello. There we go. Double tap. Virtuoso. So the DRC is probably one of the best tools in the world. It's Pegasus, and I really like Pegasus. I'm a Asura and Diva guy, but Pegasus has been pretty good. I really enjoy the way it like tests for like so many rules. It's really cool. Let me go to my library. And I'm gonna show you guys an example of something I was seeing. Not this one. What was I doing in class? Was it this one or this one? High pass, my low pass filter. Can you see it? PMOS amplifier, Kermier, my inverter. I thought I had a low pass filter. I guess I don't. Let me go to my tutorials. I'm gonna break something. Okay. So here is one of the errors I saw, and I can tell some. Okay, I'm not making class like mandatory, to show up. I give you guys that freedom, and I record the videos, okay? And I think the last one, hopefully they were all posted. The way I publish it is I upload it, but I keep it private. But then I have to turn it public. So if something's wrong, please email me, okay? I think one of my YouTube videos was doing something funny. But anyways, I try to not to make attendance mandatory. But after what I saw with the last assignment, I don't know. It's way too late to start making things mandatory. Should have done it from day one, giving everyone daily quizzes. I wonder what the daily quiz would be. Anyways, actually, wait. It's good to turn on your cadences. I don't blame you guys. It's been a while since we played. Well, kind of. I told everyone just relax over the spring break. Me too. I wasn't relaxing. I was working. Let me see. Where was that file? My display options. Choose. Load from. Boom. Okay. Remember this stuff? Everything I go over in the videos I'm going to say it. It's the answers, okay? It's the answers to the thing. But I'm not trying to say copy and paste everything I say and be like boom, 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 and done, and you didn't learn anything from class, right? I want you guys to understand why I do it. And I know the best way to learn is by trial and error, but cadence is a tough tool. It's a really hard tool, and it can be a frustrating tool. And you'll spend like I spent I think a week literally on this assignment right here. And then when I realized, it was a schematic issue, I fixed it and I put it in the lab manual, right? And then you guys, the headache was maybe like, I don't know, 30 minutes of your life to finish the assignment compared to a week. So I try to make it really fun for you guys. I try to make it like really engaging, like as painless as possible. But when I'm getting someone getting like a weird DRC error, I'm gonna generate it. Let me see. I'm gonna do Q. Don't do what I do right now. Let me see. Let's see what metal he used. I really don't know. He probably used, I think he used this one. Because we also have people here too. Yeah, sure, whatever. Okay. Actually, no, because then it's gonna complain. I'm gonna put it on. Was it oxide? Yeah, I'm gonna put it on oxide. Whatever. Okay, I'm gonna generate a fat error. This is gonna be the worst one in the world. So I'm gonna save. Okay. So I saved the error. Whoopsie daisy. Run DRC. Okay. Run directory. I'm gonna generate an error. We're gonna throw it in my DRC runs. Okay. Rules. This should start coming to you guys as muscle memory. All right. Just like solving for what do you call it? Voltage dividers. Submit. Boom. You guys remember voltage dividers? Miss them? Yeah, I miss them too. Now you guys have to do some crazy transistor theories, and there you go. It didn't generate an error that I wanted to, but look, I'm just generating an error. Okay, I saw this in the homework assignment, and I saw this color. Let me see. Where is it? I saw this color as a rail. So I think the student, all they did was just clicked on random, like, I don't know, like this or something, and started drawing and didn't pay attention to what they were doing. But yeah, I saw this as a submission, like this. And then they posted this, and they're like, I don't know what happened. Well, click on it, okay? Click on this. Let me see. Oxide must be covered by N implant or whatever this thing is, right? But let me tell you this. If you throw this into ChatGPT, right? You throw this into ChatGPT. ChatGPT is going to tell you, hey, let's solve this problem, right? Right? Should I show you guys an example? I don't want to. It's going to try and fix this description, this rule, right? Right? Because I'm like, help me, chat, right? Fix this problem. But let me tell you, the difference between an AI robot, maybe a technician, technicians are smarter than that. Someone who doesn't know what they're doing, and an engineer. Well, AI doesn't know. They can't reason. But what's his name? If someone doesn't know what this metal is, right? It's actually not a metal, it's an oxide, right? But you are an engineer. What is this? This is an oxide level, right? So first off, there's no point in fixing the rule, because the first rule is, well, why is this looking like this? It shouldn't. Let me see. My cadence crashed a second. Let me just go back here. Layout. Okay. You guys know that this right here, it's breaking a rule, yes, but it's like breaking a conscious rule that even cadence can't tell you, because this should be metal 1. Okay, metal 1, apply, okay, and then go here, Q, boom, metal 1, apply, okay, save, and let me see if I can do this. I've never done this. Rerun, see if that works. Oh, it worked. Oh, that's great. So you can close the layout, but still have the run thing, and then reopen the layout, because someone was also complaining, saying, I did not finish the experiment because my cadence kept crashing. If you're doing it at home, that's maybe a thing I can't really help with. But if you're using the UNLV Wi-Fi here and it's crashing, please email me. Let me know, okay? Because that means something else is happening, okay? I'll have to maybe reset your cadence or something else, okay? If you're working from home and it crashes all the time, maybe something wrong. There's something, a firewall or your Wi-Fi speed or something, okay? Or maybe you have to use a VPN. But anyways, cadence crashing shouldn't be an excuse for not finishing the assignment, okay? I'm sorry for saying these things, but anyways, here's this. Let me see the run. Boom, DRC is good, right? Pretty chill. And then I'm not going to do the LVS because it's already as painful as it is, okay? I gave you guys answers. That's all I wanted to say. Everything I teach you guys in this class is more like, this is how we use the tool, And then I just create an assignment, solve using the tools to solve the answer. Any questions? What about assignment 4? You guys see my announcement? Announcement. There it is. Okay. Lab 4. This is what I'm kind of trying to do. I wonder where my other announcement went. It's okay. Remember how I went over the last class where I was like we're creating an NMOS current mirror, right? And then I think I showed you guys LT Spice stuff. Ah, shoes, I gotta upload the LT Spice. Create an NMOS current mirror using the minimum size, right? You guys know what minimum sizes are? Defaults, the smallest width, smallest lengths. And then create an NMOS current mirror where you multiply it by 5, right? I did this all last class. Remember? You guys were here, right? Leo, you were here, right? Last week?
No, but I watched the video.
And it was good, right?
Yeah.
Thank you. See, actually, that makes me really happy because if you don't come to class, it's fine. But if you watch the video and then I'm like, you like it?
Yeah.
Straightforward, right?
Yeah.
Thank you. I didn't go over current PMOS, but I'll do the PMOS today. I'm giving you guys too many gifts. You guys like that? Create a PMOS current mirror. And remember with the LT Spice simulation, we had to buff the PMOS by like 2 times, right? Because of the, electron drift, the speed, or what do you call it? I think it's called electron drift. I forget the word, but basically the PMOS uses holes to like generate a current or mimic a current, whereas NMOS uses electrons, okay? So things are slower in a PMOS than it is in an NMOS, all right? So you may need to increase it, okay? And maybe I should make the requirement, make the current the same as the NMOS. Just you tell me, okay? That's your investigation. I haven't done it yet, but I'll do it today, okay? And then multiply the PMOS thing by 5. You're going to create 4 unique cells, correct, right? And then make a rail system for them, VSS, VDD, and sub, right? And then I put the bonus question, create a new schematic, my current mirrors, and just put them all together, like link them like Legos, right? And then have this cool like a symbol saying, here's all my outputs, output NMOS, NMOS output times 5, PMOS, and PMOS output times 5, right? And then boom, you can put that on a chip, yeah, and give it to the next chain of command and say, hey, here's the layout for a current mirror or a current source, right? You wanna mimic a current source, right? Or a voltage source? You got it. Sounds cool? Everything I try to teach you guys in this class is very fun, all right? So let me go to my library. Let's go back to what I did last class. Your answer to your homework. All right? Everyone understand this? No, I don't have to go over this again. All right? I'm going to go over the PMOS. Okay? Everyone can do this. Everyone can watch the last week's video. Good. Here's the output, right? Output current, because this right here is my controlling current. How do I control the current? By choking this resistor or, I don't know, making it lighter or heavier, right? Current controlling, right? If I wanted to, maybe I should have made this the other bonus question. Replace this this resistor with an active component, a PMOS, and then have an input called control or current control, and then you can control this reference and the output. Wouldn't that be pretty cool? But personally, that's way too advanced. Or not, it's not advanced, it's easy. I'm already losing people from like, oh, I can't even do the LVS. I'm like, I don't want to. See, I want to do cool stuff, but anyways. Let me give you the answer to NMOS 5. What's the difference? See this little 5 right there? How'd I do it? I'm going to record this, okay? Someone's going to complain to me an hour before the assignment due, and I'm not going to reply to that email because I'm going to be at Applebee's having happy hour, okay? Where's the answer? Right here? Multiply by 5? King of copy-paste? Right? Maybe I should be king of copy-paste because I think Dr. Baker was king of trivial questions. Anyways, create symbols, right? And then let me see. Did I simulate this the last time? I think I did. Let me see. Schematic. Right? That's your simulation. I need everyone to put their simulation circuits, okay? I think everyone here did it. Yes, everyone did. There was some person who didn't show me their simulation circuit. Like I think well, first off, I want to see this. Okay? I want to see this. Like what are you working with, okay? Like what's the piece? All right? It should make sense, right? Show me all your work. But someone didn't even show me not they didn't show me this and they didn't even show me that. Because you know what I want to see? I want to see what this is doing, okay? I want to see this, okay? Because someone, I think, because remember the MIM cap, or not MIM cap, the MOS cap, right? And you need to have a DC bias, right? And some AC magnitude, right? If you don't add like 800 millivolts or 900 millivolts, you know, the VS or the threshold voltage of the NMOS, it's not going to work. The MOS cap's not going to work. Answer to the bonus question for lab 3. Needs to be greater than the threshold voltage, the DC voltage, right? Easy. I gave the answer again. Okay? So I want to see stuff like this just so I can investigate this too. I'm performing a mental DRC or LVS in my mind when I grade your guys' assignment. So if something's wrong, please show all your work and then I'll fix it. Okay? I'll give you my comments and then you guys can go home and take the 9 out of 10. Anyways, easy simulation, cool. Now let me just launch it. ADEL. Okay, I know I'm boring everyone. It's okay. If I am boring you, it's okay. That means you know what's going on, and I'm proud of that. But if you don't get it, it's that's what I'm here for. I'm here to help you guys. There we go. Let's rerun the simulation again. Run. There we go. Maybe I might show you guys something cool with this circuit. Okay, let me see. Did it run? Let me see. It did run. Okay, sorry. What's the reference current? Right here? 20 microamps. You guys see that? Can you see that?
Yeah.
20? Okay. Yeah. There you go. And what's the output current? 108 micro, right? About 100. So what's the factor? 5. Is that cool? And then I think Dr. Baker, and I don't know if Dr. Ming Zhu is doing this, but Dr. Baker is like, God, he's a mastermind. He creates these cool circuits. He even does like a talk about mismatching in current mirrors, because current mirrors, you want them to be perfect. Okay, if they're multiplying by 5, 10, 15, right? It like if you have 10 micron, right? You want the output to be 100. You need it to be exact, right? Because you're biasing something else in the future, correct? Dr. Baker goes over this lecture on how to make it perfect, like add a cascode resistor or cascode. Like, okay, you know what cascoding circuits are, right? Where if I added let me just get out of this guy. Let me get out of this guy. I really don't want to go over it, but I think I need to show you guys because I think I might be the. Let me see. Current mirror. I'm gonna copy paste this, okay, just for educational purposes. Current mirror NMOS cascode. Okay, I'm giving you guys your education's worth the way Dr. Baker would loved it. Okay, schematic. What am I gonna do? Let me see. Let's see if David remembers his CMOS education. Because I want to do this, but let me see. Cascode. If I do this, do I want to cascode this? Yeah, sure. I'm going to show you what I'm going to do. And then I'm going to copy paste this. See if David remembers his CMOS EDU education. See if it was worth it. Yes, it was. Boom. Something like that, right? Buffing the output. Right? Did Dr. Ming Zhu tell you why cascoding stuff is good? Oh, he didn't. It's to make the output resistance really high, right? So you guys remember your IV plots for, what do you call it? Remember back in 220? Or was it EGG 101 or something like that? where you had an IV plot, right? And you knew that this right here means 1 over R, right? The slope, right? And that's a resistor. Is that good? But then let's say I do, and hey, by the way, we have cookies up here. Go ahead. Let's see, I wanted to do this right here, right? What if I had IV, right? Let me just grab another color. So Dr. Mingsu didn't go over output resistance, right? And why that's important? No? No? I love teaching. Let's say I have this, okay? It's at a voltage, I don't know, 10 volts, right? What's this? It's a voltage supply, right? Right, because right here it's also 10 volts right there, 10 volts right there, right? Does that make sense? But this right here is 0 milliamp, right? This right here is, I don't know, like 10 milli, right? Minus 10 milliamp. Is that correct with everybody? Do you like how I'm teaching it? Simple, easy little things. You wish Dr. Mingsu did this? Make things a little easier. Okay, let me show you this. What if I had the following? Excuse my bad drawing. So what's this green line? Current source, right? Current supply. So right here is what do you call it? I'm gonna do. It's gonna look so bad. No, I will. I'm not gonna make hard. 1 milliamp, right? I'm just gonna say 1 milliamp. What about the current over here? Right, 1 milliamp. Same thing right here. 1 milli over there. But what's the voltage over here? Or what's the voltage? 10 volts, right? What about here? 0 volts, but it's still sourcing 1 milli or 1 milliamp. Is that making sense with everybody? So remember that one talk we had, lab 1, was it lab 1? I think it was lab 1, where we were doing NMOS and PMOS simulations, right? Where you guys saw the IV plots of a transistor, and you guys saw something like this, right? Was it ID over V? What do you call it? VDS, where VGS was equal to, I don't know, like V threshold N or something like that. Making sense? Right? And then you see how right here is our triode region. I'm going to use different colors. Right? Does that make sense? And if you zoom into this right here, right? If I were to redraw this, and it kind of looks like, right, a resistor. Make sense? Or what do you call it? The ohmic region. I'm going to draw it like this. Right? Makes sense? Everyone's understanding that transistors can be used as a resistor, right? And then I'm going to use a different color. How about this region over here? Saturation, right? Making sense? And then if I were to do the zoom out right here, it's going to look like that right there, right? Kind of looks like that. And then the 1 over R starts looking like, if it were a straight line, let me just do a straight line like this. What's a straight line compared relative to, well, I don't know. What does that remind you of? Current supply? Right? Right? So, you see how this is skewing, like going up, right? It's not a perfect current supply. So, how do I make this line, flat? I need to make R go to infinity, right? So that this value can be, no, wait. Is that correct? No. No, this needs to be a slope of 0? Hold up. I'm blanking out. Give me a second. Because if this goes to infinity, right, then this goes to 0, right? Right? Does that make sense? So output resistance High, right? Very high output resistance. So this needs to be like this. This right here is 1 over R, where R is equal to 0. Or no, infinity, sorry. Does that make sense? This line right here. Right?
If it's a straight line, wouldn't the slope just be a constant at whatever value the resistance is at?
Right here?
Yeah.
Yep. So when it turns into the saturation region, right? That Q point or whatever he's calling it, it's going to stay right there and just boom. And it's going to be at, I don't know, 10 microamps, okay? So we want very high output resistance, correct? So this is where I think Dr. Baker was like saying, hey, what if we just did the following? Instead of 1 NMOS, we did 2, right? And then I did the following. I think he did this. Let me see. Was that what he did? Yeah, I think that's what he did. Let me see. I'm trying to remember what he did. He did a cascade thing. And I think that's what I'm trying to show you guys. I don't think I want to show you this. But let me see. Let me see from the good old textbooks. You guys have your CMOS EDU books. Okay. Cascode, NMOS, Curmier. There it is. Is that cool with everybody? That's kind of what I'm trying to get to. And then let me see. Okay. Now I'm remembering. Okay, this right here. This is actually from the Razavi textbook. So you have one cascode here. You have another cascode. Okay, I remember this now. Okay. Actually, this right here is bad. But yeah, that's what I'm trying to do. We're trying to cascode things so that we can, like, make things a lot easier. So if I were to show you the following, I don't want to talk too deeply about it, but you see this right here? Let's see if I can fix this circuit pretty quickly. Oh, shoes. U, there we go. And then I'm going to do S to stretch. S to stretch. Or does it move to stretch? Yes, it is move. You see that right there? I'm going to move again. Okay. And then I'm going to do the following. Copy paste, right? And get rid of this because this looked wrong to me too. There we go. Oh, you. Escape is your best friend too. Okay. Come on. Right there. Do the following right this. Boom, 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 boom. You guys like my messy circuit? It sucks. Right? What's the voltage from here to here? VGS. Right? This is why I didn't want to show this. But it's good for you. Is this good for you? Because Dr. Mingzu is not doing it. That's concerning me. It's okay. Page 3. Right? When I see this right here, right? It's automatically in saturation, right? That transistor turns into saturation, plus minus VGS, right? That makes sense? And it just kicks this into like the threshold voltage, or actually, let me see. What? That scared me too. Anyways. VGS, right? What if I do the following right here? What's the voltage right here? VGS. Does that make sense with everybody? So what's the voltage between here and here? If I were to probe it like this. Did Dr. Mingzu taught you this? No? Okay, come on. So let's just say VGS was equal to, I don't know, I'm just going to say it. Oh, God, I don't like that either. Do I want to show you that too? That might not be good. What was our threshold voltage in our assignments? Was it just 600 millivolts or something like that? Was it 600 millivolts? I think 650 or something like that. Let me see. I'm trying to remember. It's okay anyways. But you start seeing that, okay, for this to both be in saturation, right? You need this one to be greater than, well, this is already V threshold N, right? You need this condition to be satisfied. Because if this VDD goes to 0, right, then of course you can do this, but it's in saturation, but there's nothing to supply that voltage, so it dies. The whole chip is gone. It's dead, right? Right? I connect it like this. This is a current mirror right there, right? The current here is going to mimic this current right there, right? What's the voltage here? Right? What about the voltage here? And then what about the voltage from here to here? Is that cool with everybody? So ideally and theoretically, this right here needs to be 2 VGS, right? Or, yeah. Because right, you see how this right here is connected like this and it's hardwired like that, right? This one's kind of floating, but ideally this should be equal this. But in CMOS, when we're doing some crazy amplifiers, it's not really. There's other things going on, and I think Dr. Baker does a really good job at showing you how to make sure this is 2 VGS. It's really, really cool. But sometimes I wish I miss them. But anyways, is that cool with everybody? I think I should keep going on with this because I kind of want to do PMOSs. Should I go to PMOSs? Yeah, because that's your assignment for the week. Let me see. But yeah, if I wanted to do, come on, save, whatever. Come on, there you go. What? Oh, there it is. I'm too lazy. There we go. That's how you would do a cascode. Easy. You want to test that at home? Go ahead, be my guest. Anyways, I'm going to do a PMOS. And then I think I'll end it there. And then I'll talk about what I want to do for assignment 5. I don't know. I'm not so sure. I'm still doubting myself about what to give you guys. Let me see. You're probably going to do this. Which, should you? Let's see. Because I'm lazy. PMOS. Someone did a copy paste, but didn't change the layout for some reason. They used the same cell, and I was like, what the heck? Like, copy paste is cool, but understand why you're copy pasting things, okay? Anyways, they copy paste the layout from an NMOS to a PMOS, but didn't change the NMOS to a PMOS in the actual layout cell. So I was like, oh no. So that was, then they were like, I got too many DRC errors or LVSs, and I'm like, well, first off, you didn't change the device. Come on. Let's see. Ba-ba-bum. Ba-ba-bum. This is what you're gonna do on your homework. Okay. Boom. Oh, you. Let's reuse this. Oh, come on. And delete all this right here. Okay. Keep this pin here. Yeah, I'll keep it there. Let me see. V bias P is gonna be there. I GPDK PMOS 1 volt. Okay. And then let's just use the minimum size for now. Because I just want to check some things, okay? Let's just paste this here. Let's see. How do I rotate in place? Oh, come on. How do I flip it? There we go. Let me do this. VDD, right? Wait, oh, P VDD, which is an input output. If you guys want to do this with me, be my very guest. It's your homework. I hear clicking in the background. That's why. It's funny. I actually encourage everyone to just literally just follow along with me. And it helps me too, all right? You're doing the assignments? You following along? Right? Yeah, don't. I really don't mind. If you guys just look at this, it's really cool. But just make sure you show your work, okay? So I can fix problems. Okay, and then let me do I to instantiate another of these puppies, okay? We're doing your assignment. Do you like it when someone does your assignment? I do. And then, oh yeah, let me just put this right here. Label VDD, okay? Boom. 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 What am I going to do to this PMOS right here? Gate drain. Where's the gate? Right there. Where's the drain? Right here. Easy stuff. And then get rid of this. And guess what I'm going to do here? I'm going to delete this because I'm not liking this either. There we go. You see these IREF and IOUT right here, right? I'm going to move this down here, okay? And then this right here, oh, come on. I don't need a VSS, but you know what? I'm going to keep it in there, okay? Just for good practice. I'll show you why, okay? This is reminding me of my internship, okay? I remember doing my internship in IC design. That's pretty good. Okay, I'm going to teach everyone my internship skills. Label VSS. Label sub. Okay. And then, you know what? Yeah, I'll put this right here. So something that I see in industry too is that people put their pins like this right here. Like any pins that need to come in or out. They put it like this. Label V bias P. L for label. And I'm gonna delete this guy. Okay, so we're making some really good homeworks right now. Okay. Label VDD. There we go. Cool. Then I can delete this kind of. Wire. Double click. Label VDD. Boom. What about this guy right here? And just connect it like this. That'll be lazy with. Cool. What am I going to do with these two guys? These two bad dudes. You know what I'm going to do? I'm going to do the same thing. Actually. Because no, because there's like a side where it's like you have this side right here. I remember. Yeah, put this right here. I'm going to do the following. I'm going to reverse this, flip it. There you go. Are you guys liking what I'm doing? Do you guys understand why I'm doing this? Just to make it look a little more industry perfection. Label I ref. And double click. Label I out. Oh, come on. I out. Click. And then what am I going to do with this? Double click here. And then, I'm making things too complicated. IREF. Out. Woo! That looks so much cleaner. What do you guys think? Is this circuit 2 or something like that? Or NMOS, PMOS, and then times 5, both of them? There's your answer. Oh, let me get my water.
So I have a question about the assignment.
Mm-hmm.
So you said what we do next week,
Yeah, next Friday.
and then you wanted us to do both, right? Well, the NMOS last week plus this
NMOS,
this
PMOS, and I did the times 5, and I just showed you this morning, right?
week. Yeah. So those two. And then
PMOS, and then times 5 it.
yeah, and then you want us to
The bonus question, extra credit, the one that people sometimes don't do, is to put them all together. You don't have to.
For what?
You don't have to.
After what?
The bonus question.
Oh, okay.
But yeah, the bonus question is just to put them all together. So basically, you're gonna do more work for an extra point.
I guess my confusion is, are we expecting a assignment PDF for this week and then?
Yeah.
That? Oh, okay.
I told you guys I was working on it, but
Right.
I haven't been able to work on it because I have other things going on.
No, I get that. That's fine. I'm not pushing. I'm just asking because I want to know.
Why'd you think I did this?
Yes, yeah. I'm just making sure. I saw that. I'm just making sure. So then,
Was that not clear?
oh no. I'm just making sure because I'm just I don't want to miss anything. So then these we just like lay out everything.
Yeah.
Do
Oh yeah, and the layouts.
Yes, right, and that's it for the assignment, and that's going to be pretty much due next Friday.
Yep, I already have one student already halfway through it.
Oh, we did.
So because I gave this last week.
Yes, yeah, no, I watched the video. Yeah.
Okay.
Yeah.
Okay. Any other questions?
Just to assure you.
Okay.
Just to assure you, because I know you're.
Yeah, because I'm not gonna add anything new. I'm really no BS. I'm a no BS person. I want to make sure you guys have fun.
Right.
Okay.
Right.
Yeah, just literally just look what I do. I tell you, I give you guys no surprises. Or unless you want the surprise to be, you know what, investigate the cascode. No, I don't want to do that. You see, because I taught you guys the cascode, but I wouldn't have put that in the assignment if I didn't show you guys that last week.
Yeah.
You see? But now that I show you guys the cascode, I could, but personally I don't want. That's more grading for me. Plus more headaches, and I don't want to do that. Plus, that's actually Dr. Mingzu's job, not mine.
Yeah.
See the problem? I'm a very fair person if you work with me. All right, there's your assignment, your easy. Actually, what happened here? I think I know what happened. Let's see. VDD didn't like this guy. Let's go check the thing. So this is what I want you guys doing because someone's not doing it, and it's really annoying me. Just look at what the thing tells you. Okay? Floating input output. Just a warning. V bias P. Floating sub. Floating net. Oh, it's just saying it's not found in the symbol. Funny. Anyway, so I'm going to do the following. It says this is floating and this is floating. So this right here is... There you go. Is that good with everybody? So that solves this problem. But I'm going to do the following. No. Oh, wait. Basic. No con. There we go. Don't you guys just like no con? Okay, but if I check and save, it's going to tell me, oops, you don't have the things on the actual schematic. See, now it starts barking at this pin, and this pin. Actually, it shouldn't bark at this one, just these two. Anyways, because I don't need V bias N, so we're not going to create a symbol. Do you know why? We copy pasted. See, this is why I'm okay with copy pasting. You just need to know what you're talking about, okay? See that right there? Sounds cool? So I can just go here, Q this. You see V bias N. I don't have that anymore right there, right? I have V bias P, right? Now it changes the name there. VSS sub. I need a pin for V. What do you call it? VDD. Do I? Or I don't think I do. Let me see. Let me see. Give me a second. Yeah, I need a pin for VDD. Is that correct? Right? So what am I going to do? Can you copy paste? Right there, right? What am I going to do? Q it. Any questions? Like that one? Get rid of it. Easy. Right? Anyways, because I might want to lay this one out, and then you guys can take care of the rest, okay? Because I don't want to waste time. Okay? So now that we have that, I'm going to do the following. I could redo the simulation. Should I redo the simulation? Yeah, I'm too lazy. Let's see. I'm going to copy paste this and call this PMOS, okay? Follow along with the video, okay? Someone's going to complain right now. They'll be like, how'd you do that? Here's my PMOS, right? Right? How do I make this my PMOS? Queue it. Go to your library. Here's my library. PMOS. Okay it. Cool. This right here was just a voltage bias or something like that. I'm gonna add a, what do you call it? Actually, get rid of this because I think I know what's going on. Yeah, I see something wrong. But let me just solve it right now, because I think this is great to know. VDD, and then I'll change the assignment if it doesn't work the way I want it to. Because if I go here, right, queue it. I see a problem. But we can easily fix that. Let me show you. Hold up. There we go. Wait, what did I do? Okay. It's okay. So I'm going to delete this. Delete this. Delete this. Do the following. Easy stuff. Do you know why I did that? Remember that LT Spice simulation? Where I had, you see this PMOS right there? Let me just go back in time. 420 lab. LT Spice work. I need to give you this file, by the way. Remember that? Right? What's the reference current right here, right? And what's the output? It's going to ground, right? What about the reference current is this one, right? But it's outputting to ground, right? And then here's your output current, right? And that's also outputting to ground. Everyone understood? All right? No complaints when you guys do the assignment and someone's going to say the PMOS didn't work. All right? I went over that, okay? So that's why I did this. You see that right there? Check and save. Control E. That's why I did this right here. Are you following along? Yes? Yes? Cool. So what's VDD? This one right here. I think we're good. I think we can run this. Launch ADEL. Okay. I'm going to, you know what? Let's see if my king of copy paste worked. Cell view. I'm going to run that current sim. Do you like it when I tell you guys to save stuff to make it easier on you in the future? I think so too. Ignore this guy right here. Transient, conservative, because analog. I out, I ref. Actually, this might be wrong. Let's delete these, okay? So this is on recording, okay? If you don't do this, okay? I'm going to grab my magic pencil. Outputs to be plotted. Select on design. The magic pencil. Click right here. Click right here. And I see well, not a problem, but you see this I0? On the YouTube video, go back like 20 seconds and compare it with this guy. Let me see. I0 / I out. I think it was the same. So I think I did it. I think I am a mastermind. All right, and then oh yeah, you see how it's still colorful like that, right? Press escape. Now the magic pencil's off. Okay, let's run it. Oh yeah. All right. Okay, everything's negative. Cool, that's fun. What's the input current? About negative 17 micro, right? What's the output current? About minus 20 microamps, right? Do you know why it's negative? Because things are coming out, right? It's going to ground. Is that understood with everybody? Let me see. What did we get for the other simulation? Give me a second. Because I'm seeing a funny thing. Or maybe I'm blanking out, but let me just... Okay. Remember the NMOS right here, right? Let's go to the schematic. What was the answer to that? I'm going to copy paste, or not copy paste. Here's my PMOS, right? PMOS, okay. Get rid of that. Here's my NMOS. You see the NMOS? ADL. Session load state. Load that current simulation. Do you like how I have everything just set up like that? Oh, this is great. Okay, here is the NMOS. And if you don't believe me, let me run this again. NMOS. Yeah, that's very interesting. Okay. But let me just check one last thing before I can confirm my suspicions. Because I don't think you have to do the thing. Let me see. 120 and 45, right? Okay? That's this is where I'm getting suspicious, okay? Here's my PMOS, right? 120, 45. This right here is 4. Okay. What do you call it? 15K. This is 15K. That's very interesting. Okay. I think I like that. I think I like that a lot. Very interesting. So this is the smallest size, right? 120 over 45, right? 15K. Control E. Let me just put this right here because I'm having a moment right now. It's pretty funny. Right there. Right there. Here's my NMOS. Here's my PMOS. Double click. This is 15K. Yeah, that's interesting. So I have the same sizes, right? And I said, oh, in the PMOS you may have to double it, but let me, because I'm getting the same currents. That's where I'm like kind of like saying, what the heck? Actually, no, it's not that bad. It's okay. Here's my PMOS right here. You see how it's close to like 20? And this right here, well, I think I need to buff it a little bit, right? So it can be equal currents. You see how this right here says, here's my IREF range. My IREF is like 20 or 19.6. And this right here is, here's my IREF. It's about 17.5. So maybe I do need to buff it a little bit, but not too much. Are you seeing what I'm saying? Right? So if I go here, PMOS, queue it, and let's just say I do the following. I'm going to do let's do 150. Okay. Just to buff it a little bit, okay? Because I told you PMOS's things are a little slow, right? But this one's actually like kind of 1-to-1. That's why I'm like, what the heck? Let me run this. There we go. Hey, looking better. You see how it's like 19.3 marker? And here's the NMOS. It's getting a little closer because we buffed it a little bit. And then how about the output current? This is the NMOS, 21, 20, right? Should I keep changing it? Yes. Let's do 180. I think maybe 180 might be nice. 180. Check and save. Run. Q this. Or no, M. It's a little too much now, right? This right here is a little more than this. So you know what? What did I have? Was it 150? U. So you know what? I think 160 might be the magic number. What do you think, Leo? You think that might be the magic number? I think so too. I think just do 160. There's your answer. But don't be exact, okay? Please don't spend like 20 minutes on this, like how I'm doing it. Is that close enough? Yeah? Hey, yeah, that's pretty close. All right, that's your PMOS. But now I want to lay this out. Okay, you guys know how to times 5 it, right? Okay, I'm not going to go over that. I want you guys to doing that for your homework. Because I think right now I'm panicking that I need to make sure I can lay this out for you guys in a DRCs. I want to catch that right now.
That's why I was asking, because I'm not the best at laying stuff out. I'm more comfortable with this, but not so much.
Exactly why I didn't want to waste too much time on things. Come on, there you go. What the heck? Get rid of Pegasus. Get rid of this. Because I don't want to waste too much time. Boom. 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 No. There you go. Let's do the PMOS, because that one might have the most problems. Because I want everyone to do this. Because if I can do it in class, so can you. I'm going to go to my current mirror PMOS. File, new, cell view. Layout. Where's layout? There we go. Let's see if I can do your homework in 15 minutes. I have students waiting for me outside. They're like, they can smell the cookies. PMOS, right? PMOS 1 volt, right? Cool. And what was the length and the width? 160. Hey, it saved it. That's cool. Okay. I'm gonna do a basic one. So I'm gonna do the following. Let me see if I can do this. I'm gonna do metal width. Let's do was it 200? Yeah, now it's beefier. Body type, it's gonna be detached, and I'm gonna do a top connection because I don't know. I don't understand how these don't work. There you go. I like this. Okay, do this. Okay. Let me see. I'm gonna do this right here too. This is for my sanity check. Okay. Boom. Let's just do that right there. That's my PMOS right there. Copy paste. PMOS 2. Boom. Move this up. I'm gonna do something crazy right now. I'm gonna go to my library and I'm gonna copy paste. Where's my RC filter? My low pass filter layout. Okay. This is why I love the rail system. Copy, copy, copy. This is what I did in industry. Move this right here. Did everyone understand what I just did? This is my rail system. Right? Is that cool? Any questions about what I just did there? This is my sub. This is my VSS. Cool. And then I might do the following for my VDD. That's my VDD rail. So this is my play field right here. You see this middle right here? That's my layout play field. Is that cool with everybody? So I'm going to do the following. Move this up here. And then what was that resistor we were playing with? Get rid of this. I'm trying to speed through this so I can finish this for you guys. But I'm gonna still make you guys do it for homework. Okay? I might I don't know. I'll think about giving you guys an extra week, but personally, I think you guys should already have the simulations done by now. Okay? So I'm still making that due next Friday. Because I want to do some other cool stuff. PMOS, schematic. It was res, ns, and poly. Let me just do this. Res, ns, s, res, ns, wait, and poly. There we go. And then what was my dimensions? You see? Go back to segment was, okay, what did we do? 15K. We calculated length. So I said I wanted 15K. Okay, 15K. And then segments was 8. Okay. That's a fat resistor. Okay. 14.65. Okay, and that's good. That's good. Okay, I like this. And then how many taps do I have? Contact rows, let's do 2. I wish I could do 3, but it won't let me. See, it just locks to 2. Okay. Won't let me. See that right there? That's your resistor. And now you start understanding why. You see this right here? Do you understand why instead of using a resistor here, we use a transistor and then a variable voltage? Because look at this layout. We lose so much space. It's a lot. And look at these tiny transistors. So that's what, if you wanted to do a research project for your final project, like how do you make things smaller? You use transistors. Transistors are the best things in the world, okay? Why do you think I go crazy about stuff like this? I don't like this. Okay. Move this like this. Boom. Because I think this is going to bark at me. I'm guaranteeing it's going to bark at me. I don't like it. Where's my plus? There's my plus. So this needs to be flipped upside down. Flip. There we go. That's my plus. Okay. And then I'm going to move this right here. Boom. Like this. Okay. I'm gonna rush this layout because I need to get it done. This right here is my source or my drain. Boom, boom, boom. Oh, escape. Come on. S. Boom. I'm going to do it like this. You guys are going to make it prettier in your thing, okay? And this right here is VDD. Okay, like this. Escape. S. Boom. Everyone agrees that... Oh, go on. That's VDD right there, right? Connected? Understood? What am I going to do right here? Oh, come on. W. No. R for rectangle. S for stretch. Okay. Which one's VDD? I don't know. Pick one. It's the same thing. It's a transistor. It's the same. S and D's are the same. Okay. Do this. Ah, come on. Like this. Boom. S. Boom. 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 And then this right here. What's this one going to be? The output current. R. There we go. S to stretch. Okay, I'm just gonna do it like that, okay? Is that cool with everybody? Move, boom. Then what I'm gonna do right here, waterfall. You may get a DRC error where it doesn't like long metals, but I think this should be okay. Okay? That's the plus right there. Here's the minus. Are you kidding me? It's up there? Oh, that's so dumb. Ah, gosh. You know what I'm going to do? I'm going to flip it on its side. I'm going to rotate it left. No, rotate it right. And then guess what I'm going to do? I'm going to flip this like this, okay? Now the plus is over here, right? And then the minus is down here. Cool? You know why I did that? Makes my life a lot easier. M, move, boom. I don't like bad layout. You know why I don't like bad layout? Because the DRC starts crying. You see that there? And I'm going to move this right here. Press M to move. Perfect. I like this. That's a lot better. And yeah, that didn't change. You see why my rail system's so nice? Things just start moving and flowing like water. Where am I going to connect this minus? To VSS, right? Like this. Where's VSS? This big rail right here. S to stretch. All right, now let's do my pins. Control P, VSS, which is keep first name, create label, input output, hide. On metal 1, don't forget it. Please don't. Okay, someone forgot it. I'm going to do right here, I'm going to do sub. Is that cool with everybody? This right here, I'm going to do it as Control P. This one's going to be I out. And I'm just going to, oh, I don't like that. Okay, right there. Right there. Cue this one. I'm going to do it as 0.4. Is that cool with everybody? Where's my I ref? Actually, hold up. It's not connected like this, sorry. Delete this, okay? Guess what? Actually, don't delete that. Stretch this. I'm rushing, y'all. I'm rushing. Control P. I ref. Right? Cue this. 0.3. Is that cool with everybody? Am I following my thing? I ref is REF in all caps. I out is OUT in underscore. Okay, let me see. Make sure the spelling's correct, okay? It's gonna bark at you for that too, all right? I think it's done. VDD. Woo! I think we're good. Right? Anyways, I think it's gonna bark at me for this resistor. Pegasus DRC. Yep, everything's good. All right, submit. Yeah, sure. This should pass the DRC. It didn't. Oh. Minimum area. Remember that thing I did in assignment 2 or something like that? It doesn't like this gate size. Oh, shoes. I didn't even connect the gates. Don't you just like it when I rush things? No, it's not good. Okay, boom. There we go. Paste this right this. Okay. I forgot to connect the gate drain connected thing, so I'm gonna do O. I'm gonna do a single. I'm gonna do a 3x3 stamp from metal 1. There we go. I like that. Hide. Place that right here. Cool. And I'll draw this bad dude going here. Is that gate drain connected? Right, Leo? How about this gate? Needs to be connected to this gate, correct? So how should I do it? Like this? Is that cool? King of copy paste. Come on, Dave. You guys like my copy paste? Easy. Go to Pegasus. What am I gonna do? Just rerun. You guys like Pegasus? Do you like that I'm doing your guys' assignment? Oh god. I need to stretch for a second. Soft check. P substrate missing. Do you know why? Remember from that one assignment? Lab 3. Was it Lab 2 or Lab 3? Lab 2. PMOS. Remember that soft check? I'll approve of this. I think I'll approve it. Does that sound good? This error, remember that? Because when we put it with an NMOS, then the error goes away. It's just saying, are you sure the PMOS shouldn't exist without a substrate? But with the NMOS, it makes sense, okay? So I approve this, okay? If you can get this, boom, go home. Now we're done with the DRC. Let's go to our magic LVS. If this LVS is, have a good day. If it doesn't, have a good day again. Boom, boom, boom. Don't forget input, geometry and text, submit, one readable file. Oh, sorry. Don't like skipping steps. I really don't. Okay. I'll submit. Run. Come on, baby. Let's go. Come on. Let's go. Come on, DRC it. I'm sweating. Uh-oh. Uh-oh. Come on. Ah! Oh. This is my lucky day. I love it. This is my internship. I'm living my internship days. Copy. We forgot V bias P. So what am I gonna do here? I'm gonna delete this. Okay. Control P. V bias P. Was V bias P an input or an output or both? It was both. Okay. Save. You don't need a DRC it. We just need to LVS it. Okay. You can DRC it on your own free time. Okay. Rerun it. Come on, baby. Come on. Let's go. I don't want to make money. Come on. Let's go. Woo, 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 woo. This should work. It's running. It's running. Man. What'd I mess up? V bias P and V bias P. Schematic is open, but my layout pin is VSS. Layout net 2, layout net. It's saying VSS, VSS, VSS. I'll fix this issue. In the schematic, it's open, and the layout pin, I think it's talking about that darn resistor. Shorts and opens. VSS, layout net, dun, 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 open. If I click on that again, it's not going to let me do the thing I want to do. Click on this. I'm on. We were so close to greatness, everybody. This is my PMOS VDD, V bias P. It's gotta be this resistor, everybody. I think that's what it's complaining about. V bias P. It's its own thing. Sub is its own thing. I think I know what it might be, and I think it's really, really dumb. I'm gonna queue this. _2. Oh, great! It disappeared. IREF, VSS, queue it. Sub, V bias P, boom. I'll figure this out. It's something very small, but I'm gonna publish this, okay, today. All right. Any questions? Have a good day, everybody.